Thank you all for joining us tonight. Thank you all for joining us tonight. The purpose of the Young Israel Shomrei Emunah Meaningful Tefilah Project is to present programs helping all of us develop greater kavanah, intention, in our davening. Since 2014, we have offered programs delving into the meaning of the Shema, Amidah, Hallel, Ashrei, Slichot, Vidui, and more, offered classes in Chazanut, and posted 40 videos of these programs on YouTube. You can find them on the Meaningful Tefilah Project channel. Tonight, we are setting out what we expect to be a year-long series intended to help us better appreciate the presence of Hashem in the world around us and in our daily lives. We welcome KMS as a sponsor of this new series. The first three presentations, starting tonight and continuing in March and May, focus on seeing Hashem's hand in nature. As Rambam says in both Mishnah Torah and Moreh Nevuchim, by studying science and the wonders of nature, we can develop and strengthen both our awe and love of Hashem. Tonight's topic is Mesader haKochavim, bringing order out of chaos in the heavens. I will introduce our speaker in a moment. The two following lectures on
choice to sign up by choice to sign up by audio computer, and you
could you please mute yourselves? The two following lectures on Sunday, March 27th and Sunday, May 8th will focus us inward on some miraculous processes found within all living beings. Next, we are planning several lectures about periods or points in history where we can most clearly see the hand of Hashem shaping events, whether on behalf of the Jewish people in particular or for humanity in general. We plan to follow those with another series of lectures and perhaps some panel discussions, discussing times when individuals have perceived Hashem intervening in their lives in ways that have enhanced their personal faith and kavanah. If you would like to be reminded of upcoming programs and have not already done so, please send your email address to me at stuartrosenthal@yais.org. Sponsors are also welcome. I would like to thank our sponsors to date, Ken and Cheryl Jacobson and Mark and Debbie Katz. We hope as COVID recedes into the background, we will be able to return to in-person programming that, as in the before times, will be followed by refreshments. We'll keep you informed. Please also tell your friends about this series and encourage them to join us. Our speaker tonight is Dr. Jeremy Schnittman, a research astrophysicist at NASA's Goddard Space Flight Center, where he has worked since 2010. His research focuses primarily on computer simulations of black holes and gravitational waves. He holds a PhD in physics from MIT and a BA in physics from Harvard. Jeremy has a passion for sharing his love of physics, astronomy, and Torah with the broader community in Silver Spring and beyond. He lives in Kent Mill with his wife Nomi, a Silver Spring native, and their 4 children. Before Jeremy speaks, the Mar Da'asra of Young Israel, Rabbi David Rosenbaum, will say some inspiring words of Torah. Also, after Jeremy's remarks, the Rabbi will moderate a question and answer session. If you have questions for Jeremy as he speaks, please type them in the chat for the Rabbi to present after Jeremy concludes. Rabbi Rosenbaum has been strongly supportive of the Meaningful Tefilah Project since the beginning. In fact, it was his suggestion that davening with kavanah is directly connected to a person's level of emunah, faith in Hashem, that really led to this series of lectures. Thank you, Rabbi, for all your help and for joining us tonight. The floor is yours.
Thank you very much, Stuart, for all of your efforts. I'm sure I'm speaking on everyone's behalf. Not only are we appreciative of all your efforts, but your creativity in constantly thinking of what new to do with the program. And this year-long project is very special and unique. And Yasher Koach to you, thank you very much. I also want to thank Dr. Jeremy Schnittman, not only for tonight's presentation, but for helping us with the rest of the science series. So thank you very, very much. Very, very brief thought. Of course, every time we have a greater appreciation of science in the world, it only deepens our appreciation of God and hopefully inspires our prayers, as Stuart mentioned. But I just wanted to reflect on one pasuk. If we're talking about the stars tonight, in some sense, so there's a pasuk that we say in the daily Psukei Zimra of the Shacharis service, Monem Mispar haKochavim, that God counts number to the stars, L'chulam Shemos Yikra, and he gives each of them a name. And it's an interesting thing to think about because, of course, when we look out at the sky, we see so many stars. And to the uneducated person, how could you give each star a separate name? There's so many of them, they seem so similar. But of course, the Mefarshim explained, the commentators explained that the point of the verse is that despite the fact that they all look so similar to us, each one has a unique function and purpose. I suppose this fits into the order of which Dr. Schnittman is going to speak in some sense. And we might not easily understand all of the order, but God certainly does. And that, the Kli Yakar says, is a wonderful parable for how God looks at each and every one of us. The Jewish people are compared to the stars of the heaven. So thank God, the context of being compared to the stars of the heaven is that there should be many of us. But as we said before, when one looks at the stars, sometimes it's hard to see the unique value in each and every one. The Kli Yakar says the same way we say in this verse, that God has an appreciation for the function and purpose of each star, so too God has a unique appreciation for each and every one of us. So as we hear what I'm sure will be enlightening words tonight, not only about the science, but about God's organizing so much of this confusing world, it's worth it to take a moment and reflect that this is also a parable for how God somehow puts everything together in our world, and more down to our earth. Things seem so chaotic, things seem so purposeless. There's tremendous purpose with all of it. So perhaps if we think about that as we're listening to Dr. Schnittman's lecture, it will give us an even deeper perspective. And I'll pass it on to Dr. Schnittman now.
Thank you, Rabbi, so much for those very inspiring words. I hope we can try to live up to some of the inspiration that you laid out and that that Stuart had in mind when putting together this series. So now I guess I'll start by sharing my slides here. Okay, so I called the talk Mesader es haKochavim, which literally means to arrange the stars, right? And this is something that we say every night in the very beginning of the Marav, of the evening prayer, when describing God as the creator, all of the things that he does to keep the world running, turning from day to night, night to day, and then setting up the stars. And you know, another theme that I think Stuart was mentioning before, or alluding to, is this idea that if we want to, right, I think this is a chazal that tells us that if we want to really become closer to God, come closer to Hashem, we should emulate him, right? Just as God is merciful, we should be merciful. As God takes care of the widows and orphans, we should take care of the widows and orphans. Just as, you know, God created the entire universe ex nihilo, we should create the entire universe ex nihilo. That, you know, how can we even begin to understand the idea of emulating God as the creator? And I think very humbly that one approach is to do exactly this, to bring order out of the chaos, to search out for these patterns, look for these subtle clues in the behavior of the stars and the world around us. And in doing so, we can begin to see really the hand of God in the world, because we know that this is exactly how Hashem created the world in Bereshis. Everything is an act of splitting, dividing, sorting, right? Dark and light, heavens and water, earth and dry land, and the stars and the day, right? So every step along the way is an act of sorting, ordering, and dividing. So hopefully today we will get to see some level of doing that, of finding some sort of order in the stars. So here's a picture of the night sky, at least roughly speaking, from the northern hemisphere. The good thing about the constellations, even in let's say semi-urban settings like Silver Spring, they're actually pretty easy to see, a lot of them. And you know, probably some of us at least can pick out the Big Dipper in a good night, or maybe Orion. But of course, the ancients knew these much better than we did, right? They had well, they didn't have TV in the evening, right? So they had a much better appreciation of these stars, and of course, whole mythologies grew up around them. But in the ancient world, other than mythology, it's really hard to see, much purpose to the stars other than looking at them, right? The sun and to a slightly lesser extent, the moon really governed all the day-to-day activities that, literally day and night, and then of course the seasons. The stars are really kind of a very abstract theoretical aspect of nature that, it's hard to see a direct impact on our day-to-day life from them. And I guess that's one of the reasons, I can appreciate them and relate so much. I'm sure many people on this call were our federal employees, and you remember the last time we had a government shutdown, they send out the email to all the non-essential employees, and the theoretical physicists at NASA are right at the top of that list of non-essential employees. And some people say, well, I wish they would give me more credit for being an essential part of the program. But I think there's something to be said, to be honest, about being quote unquote non-essential, of being able to, the great fortune that I have of being able to spend my life looking at these things that I guess in Hebrew would say lishma, right? Studying things for their own sake, as opposed to, having to rely on them for when to plant our crops or park, where to park the car every day. So here's the stars, and as we can see, the ancients in different cultures, but pretty universally around the world, kind of basically just did dot to dots. They lumped them into shapes and figures, and this is a very natural thing to do for humans, to look at random dots and pull out patterns from them. This will be a recurring theme that we'll see throughout the talk. Again, how do you make sense of what could otherwise seemingly be a random collection of dots? Here's another way of looking at those constellations. This is now plotted out in what we call celestial coordinates, right? It's like if you were to take the whole sky around the Earth and plot it out just like a Mercator projection of the sphere of the Earth. This is essentially the Mercator projection of the sky, where the whole line at the top is the North Pole, and then there's the equator straight through the middle, and the South Pole at the other end. And this dotted orange line is where the sun moves through the sky throughout the year. And so this, right, a lot of us are familiar, we're probably not avid horoscope readers, but we know about the basic 12 different horoscope signs. And those just correspond to, when you were born was when the sun was going through your little section of the sky. So let's see, where am I? I'm a Scorpius. I don't know if you can, I doubt you can see my mouse, because I can't even see my mouse. So, but whatever, there's Scorpius. So for, the month of the year that the sun was in that area of the sky, that was, September, October time of year. And the kind of the important points to raise here, I guess, are that this line where the sun goes, what we call the ecliptic, right? The path through the sky of the sun is called the ecliptic. It doesn't line up with the equator, right? Sometimes it goes to the south of the equator, sometimes it goes to the north of the equator. And then at the equinoxes, it goes right in the equator, right? It's not a coincidence, right? That's why they're called the equinoxes. So the ancients looked at something like this, and they were able to use those background stars, first and foremost, not necessarily to find order in the stars, but to use the stars as like a background grid, or like a piece of graph paper, essentially, to find the order in the sun. So they could carefully measure how the sun and the moon moved through the sky relative to this essentially fixed piece of graph paper. So that was the most important thing about these constellations in classical astronomy, was how you could use them to in fact study things like the sun, which of course had a much greater direct impact on everybody's life. So now we're going to go through basically the whole 2,000 years of astronomical history leading up to today in hopefully under 45 minutes. And we'll start with Ptolemy, who was lived in 1st, 2nd century CE. And he was really the first one to lay down a real, what we would think of today as a model, a mathematical model to explain how the sun and the planets and the moon moved through the sky. And of course, the stars too, right? The stars were considered to be on this literally a celestial sphere that surrounded the Earth and rotated every day, which is why they, move through the sky. And he basically got a lot of his background from a Greek astronomer, Hipparchus, who lived about 300 years before Ptolemy, and did a lot of great observing, but didn't really wasn't as strong in the mathematical models. So Ptolemy took 300 years worth of observations, starting from Hipparchus up to his time, and compiled them together in this book called the Almagest, which was, just tables and tables of numbers, and then formulas essentially for how to translate those numbers into predictions. And here's just a very simplistic picture of what his model looked like, right? This is, of course, we know that the ancients used a geocentric model where the sun and the planets and all the stars orbit around the Earth. But something that a lot of people don't appreciate is the geocentric model wasn't actually geocentric. I mean, it was roughly geocentric. The Earth was roughly in the middle, but the sun actually went around a point that was off center, right? If you think of in this little picture, right, G is the Earth, geo, but the sun was going around this point C, the center. In fact, that little offset was called an eccentric. It wasn't in the center, it was eccentric. So the sun went in an eccentric orbit around the Earth. Also, I wanted to remind everyone that despite what you might have learned in 2nd grade on Columbus Day, 2,000 years ago, everybody knew the Earth was round, right? This was not a question. There were so many different ways, even a guy just living as a farmer in ancient Greece would have known that the world is round. It was not very controversial. So that was his simple model for how the sun moved around the Earth, and that worked out pretty well. When it came to the planets, he had to get a little bit more complicated. So the planets would go on these little epicycles on the circles. So they would go on circles around the Earth, and then they would go on little circles around the circles. And that was needed in order to explain the kind of complicated trajectories of the planets through the sky. Similarly too with the moon, here's a picture of how the moon would go around the Earth. Here we've got the Earth is in the little center in the crosshairs. And I don't know how well it shows up on your screen, but at the very top of this diagram, there's a little circle with a dot in it. That's the sun. And then beneath that, there's a little, a moon shape. And sure enough, that's the moon. So the moon also went on a little epicycle around its circle, and then that circle went around the Earth. And that was all still what he was getting from Hipparchus from 300 years before. And it was an okay model. It wasn't great. One of the best things about it was not the little details, but the big picture of how the moon went around on this big circle, which is called the deferent. And that big circle is what we can think of as like the average moon's orbit. or as anyone who was in shul this past Shabbos would have heard about the announcement of the Molad. And the Molad is 29 days, 12 hours, and 793 parts. That's 793 out of 1,080 parts of an hour. So something like 20 seconds. No, something like 3 seconds. So a part is something like 3 seconds. Yeah. So the incredible thing is this number that we use still in shul today and for all of our calendars dates back to the times of Ptolemy and Hipparchus. And the number that, essentially that they had and the one that we still use today is accurate to the best NASA calculations and observations of the moon to better than 1/3 of a second. So that's to me, this is one of like the most amazing things about the Jewish calendar is that frankly, like every year we go out and eat in the sukkah on the 15th of Tishrei, and every year it's a full moon, right? There's not really any reason to believe that this would still be working, that like this calendar that was essentially set down 2,000 years ago is still working to, much smaller than a fraction of a day today. So I think that's pretty cool. But even that was not good enough for Ptolemy, right? Because it only gave you the average time of the moon. And the moon, frankly, does a lot of weird stuff. It's much less well behaved than the sun. In fact, I'll probably butcher the pasuk, but pasuk in Tehillim says essentially that Hashem made the moon for the holidays, and the sun knows its path. In other words, the sun is going to do what the sun is going to do, and it's very simple and regular. But the moon is for the holidays because we need to pay extra attention to the moon. You can't use it. It's not so easy to predict the holidays, right? That's a whole nother talk that maybe we'll get into next year about how the Beis Din did the lunar observations and the witnesses and all that. But it wasn't easy. So Ptolemy had to go from the Hipparchus model to a somewhat more complicated model. And his basic tool was, if something doesn't work, just add another circle, right? So he just built up this whole model of the universe, of the motion of the moon and all the planets by adding circles on top of circles. So now we've got a circle that's going around a circle, but it's not connected to the center circle, not connected to the Earth, but it's connected to a different circle that's going around, a little circle that's going around the Earth, connected to a big circle that's going around the Earth, and then a little circle that's going around the big circle around the little circle. Okay, hope it's all clear, because Ptolemy did this on like a stick with a sand floor or something. So hopefully we can follow along. I'm just going to take a second. I hope this works. So this is this whole model of Ptolemy, which is what ultimately was inherited by the Rambam, who then uses it to describe in great detail how the moon calculations are done. I actually spent quite a lot of time working on this last summer with some students from Stern College, and I've got a program here that's supposed to illustrate how this worked. I hope you can still see my screen. There's just nod if you see kind of computer program looking things showing up. Let's see. You see a lot of circles and sticks moving around? Okay, great. So this is, and now hopefully you can see my mouse too. So here is that model of Ptolemy in action. So you've got the Earth in the center, you've got the sun moving around this outer circle on a little eccentric circle, and then the moon going around the Earth on a much more complicated combination of multiple circles. And then I also have it kind of tracing out the path as it goes along. So you can see the sun out here, and these are actually used the exact same numbers that the Rambam includes in his Kiddush HaChodesh from the year 1100. We plug those numbers in, and it starts at Nisan, where the sun is over here in the literally in the east. In fact, today that's the definition of the eastern part of the sky, is where the sun is at the equinox in the spring. And then it goes up here through the summer, kind of goes up what we would call the north part of the sky. And then you see the moon doing all these complicated procedures here. And whenever you get these line up of the moon, boom, right there with the sun, that's like the exact molad, not the average molad that we announce in shul, but the exact molad that they would use to essentially interrogate the witnesses to know when the new moon is going to happen, when all the holidays are happening. So you can understand why, if you want to get all that right, you really need to have a very comprehensive understanding of where all of these objects were going in the sky, and a really good understanding of Ptolemy's celestial model. Of course, this is just a picture of what it would look like, kind of, the angel eye view of the solar system. The Rambam was also interested in how do we actually calculate whether a person living in Israel could see the new moon right after sunset. So he goes into all the calculations how to do that too, which I tried to mock up in this little picture. And maybe illustration isn't my strongest suit, but this is roughly a picture of what the western horizon would look like right after sunset on the dates surrounding the new moon. So kind of see just these flashes. It's a little too complicated to get into now, but essentially this was all known well from the days of Ptolemy, and then explained in great detail by the Rambam in 1100s. So they essentially knew how to calculate to a fraction of a degree where all of the celestial objects were going to be at any time. And of course, in that case, now we're getting back to the very practicality of thing of, told you when Pesach was. It's very, very, very important that if you're not going to eat chametz on Pesach, you have to know when Pesach really is. But I think, right, for kind of the average person, right, any of us who aren't sitting on the Sanhedrin in Yerushalayim, there is also a lot of value of understanding these patterns and these formulas and these calculations, because like we started out with, this is exactly what it is involved in order to understand God's world better and to grow closer to him. So now let's jump back to the talk. So that's Ptolemy. Here's another picture I drew of kind of putting it all together. The other very impressive part of the Rambam's model is that, again, if you plugged in the numbers that he provides, essentially starting in the year 1100 and working our way forward, I did it just kind of as an exercise leading up to the first of Tammuz 5780, which was my son Chaim's bar mitzvah. He was born on Rosh Chodesh Tammuz, and that was essentially the day and time that he became a bar mitzvah at 9 p.m. on that date. And this is what the sky looked like. This is where the sun and the moon were at that time. And if you actually go to the JPL, the Jet Propulsion Laboratory's website that tells you where all of the planets and stars are any moment in the sky, you can see the sun was only about a degree off from where the Rambam predicted, and the moon was less than even a quarter of a degree difference from where the Rambam predicted it, 900 years before. So that's a pretty good model. Jump forward okay. Jump forward a few hundred more years to Copernicus, who is, as probably many of you know, Copernicus was the one who essentially made the push from the geocentric model to the heliocentric model. And he was, I mean, he did some observations. He did, you know, especially in those days, you weren't just a theorist or just an observer or just an astronomer. You know, he was also, you know, an anatomist and a doctor. He did everything, but mostly I would say he was like what we would call today a theorist, right? He looked at a bunch of published observations of the planets and the stars, and from that he essentially just came up with this model on his own, and then kind of retroactively, yeah, this is what I've heard. There are other people who are really much better historians on the subject, but I think he kind of retroactively found a few outlying Greeks that also agreed that you could have a heliocentric model. So for him, it was a better model of the solar system because it was simpler. It explained some of the motions of the planets that were very confusing otherwise. But if you kind of look at it as a sketch, on a certain level, it's not really any simpler than the geocentric model. And at this point, you know, really, it was kind of hard to compare the two models and say, you know, to us, it's like obvious that Copernicus was right and everyone before him was wrong. But at the time, it wasn't really obvious that either model was better than the other, right? They both were able to make the predictions or the explanations of where the planets were, and they both had some problems, and they both needed a lot of these complicated pieces, right? You see this, they still had the epicycles around the epicycles, and of course, neither of them had any explanation for why any of this worked, right? They were all really just descriptive models of how the planets moved, but not really any deep understanding of how of why the planets moved like that. So in the typical timeline, we go from Copernicus to about 100 years later. Tycho Brahe was like a real observer. He was like one of the best observers. Well, he was the best astronomical observer up to his time. In fact, one of the things his first book, De Nova Stella, is about the new stars, and he was an observer of supernova. So basically, new stars that would show up, right? A nova means new, right, in Latin. So he was very interested in these new stars that literally appeared out of nowhere when they became. Now we understand them as supernovas. Which also was, you know, in his version of Catholicism, was like really heresy, this idea that anything could have changed in the heavens. So that was, you know, kind of remarkable that he made that all the work about having new stars in the heavens. But at the same time, even with all of his extensive and very detailed observations of where the stars and the planets were, he actually was a little bit of a throwback from before. He never liked Copernicus's model. He liked he had like this. So he had this like hybrid model where he agreed that the planets could go around the sun, but the Earth still had to be in the center. In fact, he said that, right, this idea of that the Earth going around the sun, not just that it was not like anthrocentric, but that like he literally thought you would just fly off of the Earth if the Earth were moving around that fast. This was very common belief of the Greeks, right? That there's no way that the Earth could have been spinning because you would have just, you don't feel it moving, right? You can feel it if you're moving on a horse or a ship, but we don't feel the Earth spinning. So it was really just like ridiculous to them that the Earth could have been spinning or moving around the sun. And it also seems to be against his religious beliefs. So again, he had all these great observations, but ultimately he didn't come up with a great model to explain them. And I think a lot of it was because he was somewhat hamstrung by these either theological or kind of philosophical beliefs about what made sense about the system. I don't remember exactly how this joke kind of fits in. So why don't we just take 10 seconds to look at this cartoon and chuckle, and then we can move on to the next slide. Essentially, right, these models are getting better and better data as they're getting more and more observations of the stars, but if anything, they're becoming more and more complicated, right? The better data doesn't seem to be making the cosmological or the solar system models any simpler, until we get to Kepler, right? So Kepler was a younger contemporary of Tycho. And in fact, he had to work really hard to get the data from Tycho. This is something that we still unfortunately have to deal with regularly today. When somebody puts in the effort to take all the data, they don't generally like to share it with other people. But he eventually wore Tycho down. He got his encyclopedia's worth of planetary observations and data, and just ground the numbers more and more and carefully, and trying to come up with more and more detailed models to fit all of these very, very accurate data. And it should be noted that Kepler was actually a staunch Copernican. He definitely believed in the heliocentric model. So maybe that was also why Tycho didn't want to share his data, because it was basically going to shut down his favorite model. Long story short, after struggling for years and years with more and more complicated mathematical formulas, he almost by luck stumbled across these three models. I shouldn't say by luck, because he really put in a lot of effort, but he was fortunate to have discovered this incredibly simple mathematical relationship. In fact, one history I read said that he initially had dismissed this model because it was so simple, he couldn't believe that the Greeks wouldn't have gotten to it first. So the fact that no Greek astronomers had mentioned this, he was sure that it was probably not the right model. It was too simple. But here's the Kepler's famous three laws of planetary motion. One is that all the planets go around the sun, and they go on elliptical orbits. They follow not circles but ellipses, which is just a mathematical version of an oval. The second one is that he saw that they would sweep out, if you kind of drew on a piece of paper, how much area that shaded size of that ellipse was always the same in the same amount of time. So if you looked at where Jupiter was 6 months apart, it was making a same size triangle wherever it was in the orbit. So what that meant in practice was that when it was close to the sun, it had to go faster because you have kind of a smaller area. So you have to sweep out a bigger arc. Then when you're farther away, you sweep out a small arc, but you have a long leg to the triangle. And then the last one was, again, just kind of figured it out by trial and error, this very tight relationship where if you just take the period, the total amount of time it takes to go around the orbit, and you square it, that was directly proportional to the size of the orbit to the third power. Again, for Kepler, it was just a numerical oddity, a formula that worked, and he really had no idea why. In fact, Kepler was famous for seeing the significance in these beautiful, simple models of what they actually, the name of his book was called Harmonica Mundi, the harmony of the spheres, which was a title based on the idea that these planets were actually attached to giant crystal spheres, and the spheres were actually physically like moving through the sky and in fact scraping against you. Even the Rambam talks about, I think it's in more Nevuchim, he talks about how if we were angels, we would hear this like incredibly loud screeching of crystal spheres rolling against each other in the sky. So here's just a little schematic in that book about the Harmonica Mundi of how you can describe all of these orbits in the shapes of the planets with simple geometrical shapes. it was very beautiful and harmonic, although we now know basically it was just a coincidence, and it was, if anything, leading Kepler down a like a red herring. It was like leading him down the wrong path, which is why he never really got further than those three basic laws, which of course were very important, but they didn't really explain why anything happened. So at this point, I think it's befitting to really ask ourselves, what are we really looking for in all of this anyways, right? I mean, Kepler was able to give us very simple laws for where everything in the sky would be at any time. I mean, that's pretty good. I mean, if you want to understand God's world, and you can literally predict how the heavens will move and behave over courses of months and years and centuries, that's pretty impressive. But it's what I would call through all of this a descriptive law of nature, right? These basically just describe how they describe how the stars move, how the planets move. But it doesn't really it doesn't prescribe how they move. It doesn't explain why they move that way. And it certainly doesn't go to this even higher level, some people call the transcendent law of nature, which essentially is that idea of going even beyond nature into God's mind, as it were, the deeper of the deep meaning behind all of this. So to get to that, we have to get to the next the greatest of the great yet, so far, probably 100 years later, to Isaac Newton, who, again, we have a whole talk just on Newton's incredible greatness as a scientist, physicist. But in one slide, he essentially took he has this famous quote of, "If I've seen farther is by standing on the shoulders of giants." So he took all of that work from the giants that came before him and did a similar approach to what Kepler did of, trying to make sense of all of these numbers. He was just happened to be much better at it, and to the point where he even invented calculus to work out all of the complicated math needed in order to work through all of this data. And he was able to reduce those three empirical laws of Kepler into a single mathematical formula, which we can now write like this. This is just a mathematical way of saying that the force between the gravitational force between two objects is just this product of this G, what we call Newton's constant, times the mass of one times the mass of the other, divided by the distance between them squared. And the n is it's a direction, and the direction connecting the two means that it's an attractive force. They're not like pushing off to the side. And that was, essentially Newton was able to boil down everything that had ever been seen, measured, predicted, and explained up to his point with a single formula, which is, really, really incredible. And it was the ultimate revolution in physics, where from that point on, for essentially the next 200 years, all the great physicists, Maxwell and Boltzmann, thermodynamics, electricity, magnetism, all of the things you've probably forgotten from high school, all were developed in those next 200 years. And they all came up with mathematical formulas to describe how the world behaved, optics, heat and energy, everything, right? The problem was they came up with, explained more and more aspects of physics and of nature with more and more laws. So now we end up, instead of drawing, having more and more kind of circles adding onto circles, now we just have laws adding onto laws, adding onto laws. And this was the situation when Einstein came around in the turn of the 20th century, and he started basically going in a different direction. He started taking all of these laws and trying to put them back together and say, well, why do we need two different laws? Maybe we could come up with just one big law. And this is something that I think a lot of us are familiar with now, this idea of like the grand unified theory. But this was a movement that basically started at the time of Einstein, of taking things that were maybe not obviously connected and putting them together and being able to explain them with a single formula. So the first example is just in 1905, he came up with the special theory of relativity, which is a way of combining space and time. We've probably heard of space-time. That was the special theory of relativity. This little formula below, we don't need to worry about the details, but that essentially replaced all of Maxwell's equations. Were these famous equations that described all of magnetic forces and electric forces, and he basically just all sweep them up into one single force. And then Einstein spent essentially the next 10 years of his life, from 1905 to 1915, trying to again unify all of this space-time with the force of gravity, which seemed to behave somewhat differently, and again was able to do this with a single formula of unifying all of these concepts that they were learning. And this one in particular, right, the general theory of relativity, this Einstein's theory of gravity, which happens to be like, my life's work is studying this. And I think it especially fits well into this talk because the two very famous examples of how he was able to test this theory right at the beginning when he first. So first of all, he came up, like the way that Einstein worked was also almost completely different than anyone else we've talked about today. He didn't go through encyclopedias of old observations. He literally just sat down with a pencil and paper and thought about how the universe should behave, how what made sense to him, and then tried to write it down as a consistent mathematical formula, and then go back and see if the universe agreed with him. And the amazing thing with Einstein, of course, was that it did, over and over and over again. His theories, which were not, for the most part, based on observations, they were completely what we would call prescriptive in this model, right? Not just describing what everybody else already knew, but making prediction after prediction after prediction of how the world should work. And again, we just kept proving him right over and over and over again. So one of them was about this, we said that Kepler said the planets go on ellipses. Well, it turns out that already by the end of the 19th century, they noticed that Mercury, the innermost planet, right, the closest to the sun, wasn't quite an ellipse. It was an ellipse that kind of twisted every time. So it makes like this spirograph image. And in the drawing here that I'm showing is a greatly exaggerated portrayal of that. It was actually a tiny, tiny, tiny effect, but they were coming up with better and better telescopes at the time, so they were able to see this, but nobody could explain it. And Einstein wasn't even really trying to explain it, but he came up with this theory, and sure enough, it worked perfectly to describe and explain the motion of Mercury. And then, like I said, he started making predictions, right? So he was able to predict that during a solar eclipse, the locations of the stars in the sky would actually be in slightly different location. That's called gravitational lensing. And they staged these huge campaigns to go out and study eclipses all over. Eclipses always seem to happen in the middle of nowhere. So it was a little tricky. It took them a few more years, but sure enough, they were able to use those predictions and again, prove his theory right. And he was just getting started in 1917. Again, he took this one kind of master formula of how planets and stars should move, and he applied it, in fact, to the entire universe as a whole, right? This was the beginning of real cosmology. So he applied this formula to the universe, and it broke. It gave it basically didn't give a reasonable answer. And the reason was because in 1917, everyone in the world knew with complete certainty that the universe was eternal, right? It had no beginning, it had no end. Anyone who thought otherwise was like a real, like we would think like real backwards, right-wing religious nut, right? Everybody knew that the universe was eternal, and Einstein knew it, and that's why his formula didn't work, right? He couldn't explain the structure of the universe because it would always want to collapse or explode. So Einstein actually tweaked this formula a little with putting in this little extra term to the formula. Again, we're not going to deal with any of the math here, but he called it the cosmological constant, really. And it literally was just this fudge factor that he had to stick into his equation in order to make the universe static, right? To make it a steady state universe, because again, everybody knew that the universe was eternal. And the only way he could get his formulas to work was he put in this fudge factor. Shortly thereafter, he had, there were a couple, I'm gonna kind of move through this a little more quickly. But there are a couple other physicists, Friedman and Lemaitre, who took Einstein's first formula, not without the fudge factor, and just followed it through mathematically and see what they got. And sure enough, they got solutions that showed universes that were expanding or contracting. Now, Lemaitre was actually a Catholic priest, so he did not have the same kind of hang up about this idea of a universe that had a beginning. So he went with this, but Einstein in the 20s basically paid them no attention. He thought it was completely absurd, this idea of a non-static universe. And at the same time, we go back to our kind of the other side of our scale, right? We always have like the theorists and the observers. At the same time, the telescopes are just keep getting bigger and bigger, and the instruments are getting more and more sensitive. And this is when Edwin Hubble made his great discoveries in the 1920s, looking at galaxies, which they didn't even know that galaxies were galaxies. They thought that everything was all in the Milky Way. But when Hubble came around, and over the 20s and really up until around 1929, 1931, he was able to measure these, what they called nebula, because they didn't know that they were outside of, they didn't know what the thing galaxy was. And they could see that the farther and farther away you went, the faster and faster the galaxies were going away from us. And this is what we call today the expanding universe. This is a common model for it, this idea of a loaf of bread with little raisins in it. Those are the galaxies, and they're just expanding. They're expanding bigger and bigger. And you know, it was clear that if you're expanding bigger and bigger, then if you go backwards, it went smaller and smaller. And it must have had at one point, a time where it was all essentially all in a single point. That's what we call today the Big Bang. And when Einstein finally saw these observations of Hubble, he looked back on this equation. He said it was my greatest blunder, right? Because if he hadn't put in that fudge factor, if he had really just trusted in his original equations, he would have predicted the expansion of the universe. Which, I mean, okay, so he still had a career that was worth probably 5 or 6 Nobel Prizes, but it would have been an even more incredible discovery or prediction than any of his other stuff, to really to have predicted the Big Bang. So he kind of kicked himself for missing out on that by sticking to his philosophical prejudices. But like I said, he admitted when he was wrong. So I like to quote the Mishnah in Avos at this point, when we talk about who is a wise man and who is a golem, and the opposite of a chacham. And one of them is Moda al ha'emes, right? He concedes to the truth. He admits when he is wrong. And this, I think, we see from Einstein as a great scientist and a great person. He was able to admit when he was wrong. So I do have some more stuff to talk about, some cosmology, but I think I would actually prefer to just cut it off on this note. This is, I think, a good point to pause. and open it up to any questions that anybody in the audience might have. So I guess, Rabbi, do you want to kind of run the?
I think it
Q&A?
would be best if people submitted questions to the chat. I think that would be best. They can chat me, they can chat you, they can chat everyone if they want, but I think that's the best way to do it under our time constraints.
Okay,
I think
so let me
so.
see if I can see this chat.
Yeah, I'll keep an eye out for the chat. There were some questions that were asked along the way, but they were very local to the specific moment. If anyone
Okay.
wants to
Well,
ask,
I can pull the slides back if
okay,
you-
so there was a question. Well, but I don't know what slide it was from.
Okay.
Yeah, I don't.
There was a question about the ellipse, what's A, B, and E, which is the major semi-major axis of the ellipse, semi-minor axis, and E is the eccentricity.
Okay. Yeah, so those are, yeah, essentially just how do you label an ellipse, right? We know that a circle has a radius. Well, it's just one step up from that. An ellipse has two radiuses. It kind of has a long edge and a short edge, and that's A and that's B. And there's a formula for the difference between them is the eccentricity E. So a small eccentricity is a circle. So E equals 0 is a circle. And almost everything in the solar system is pretty close to that. Like Earth's eccentricity is 0.017. So you can understand why they basically were able to ignore a lot of it for many, many years. And Mercury actually has one of the highest eccentricities of 20% of anything in the solar system, which is one of the reasons why it was actually such a good test that its ellipse was moving, because if it was a perfect circle, we wouldn't have noticed. So I hope that helps that.
Yeah. I don't think there's any other questions in the chat that I can see. How would things be different if the Greeks? Okay, so someone put in, they would like to know more about your research on black holes and gravitational waves and how they expand our understanding of the universe.
Okay. So at least in the context of, again, a whole nother talk, but and like I said before, I'm not really a historian of science. I find history fascinating, but I probably got at least a couple of things wrong, even just on the history tonight. The black holes and the gravitational waves are more my expertise, but I think in the context of what we talked about tonight, the most important thing about black holes and gravitational waves is, again, they are two ways of testing Einstein's theories and pushing those equations that we really briefly just flashed up on the screen. Some of those equations kind of like pushes them to the limit. So when we tested them with the eclipse in Mercury 100 years ago, that was really only using them in the very what we call the very weak field regime, right? Even the surface of the sun, the gravity is like negligible compared to a black hole. So those were kind of the first simplest tests. But as we can push closer and closer to the extremes of black holes and gravitational waves, essentially it's just all a way of saying Einstein was right. And because he was able to essentially describe this entire universe that we know about all in a single beautiful equation, I think it's very meaningful to see that, yes, in fact, as far as we can tell, each and every time we tested, that is in fact the description of our universe. And that was what I mentioned before, this idea of descriptive, prescriptive, and transcendental. I mean, this is essentially a transcendental law of nature that it's like looking behind the curtain. It's seeing really to the very edges and the depths of the world around us, and seeing into God's world. So That's maybe I'm inflating my day-to-day job a little too much, but that's what keeps me going with the black holes.
I think that's very beautiful. And I think it leads into, there's a number of questions in now, but somebody posed a question. They'd like to know how you balance being a scientist and a believing Jew. Maybe that fits well with what you were talking about a moment ago.
Yeah, I mean, I hear that a lot. I think we probably all learned maybe a little too much in school, that there's some sort of conflict. I just saw a quick comment in the chat about Galileo, being condemned by the church. So I think everybody who hears that story just assumes that there's a conflict, right? I think that my whole story with Einstein in the Big Bang shows that the more we understand, the less conflict that there is, right? This idea that there used to be nothing and then there was something is a very, very core part of our belief. And it used to be actually ridiculed, right? This idea that you could literally make something out of nothing. But that's exactly what we seem to be seeing more and more, the more we understand the Big Bang. So from that point of view, I have really no problem at all. The more I know, the more I understand, I think the stronger my faith can become.
Thank you very much. Thank you. It's very nice. And if I may, maybe one of the last things we'll say, somebody wrote in, and I think we have a wide range of interests on this Zoom. So one person wrote in, as magnificent as the universe is, I'm more impressed by the insight, wisdom, reasoning of people who saw patterns, similarities, and differences and discern great insight into the way the universe works. To be honest, I was thinking a similar thing. In other words, you're really speaking about two parallel beauties, the beauties of the universe and the beauties of the human mind and figuring it all out. And I think many of us were struck by different aspects. I think it's very, very kind, very special. Thank you very much.
Thank you. And, I mean, if I may, the very fact that, right, the fact that the universe is figure outable, right, that didn't have to be, that also seems like a very precious gift that God gave us. He made this world and he wanted to not just share it, that we could live in it, but he essentially leaves little clues around to understand it and him better.
Thank you very much. Maybe we'll just end with one more question. My apologies to everyone who didn't, but I just don't want to hold people on too long if you think that's reasonable, Stuart. One more question. How are observations from the new James Webb Space Telescope predicted to adjust the current theories of universe expansion and age?
Great question. But I think, first of all, Stuart, I think since we're recording this, it should also record the chat that usually does that.
I think so.
So if you want, I can't promise everything, but Stuart, if you send me a copy of the chat, I will try to get back to people on any questions that were typed in there that we didn't get to.
Could I just, is there an email address that it's all right for people to send to you, just in case you don't know how to contact them from the chat boxes?
Sure. So it's just my last name, Schnittman@gmail.
Could you, Schnittman is spelled SCHNITTMAN @gmail.
There.
Sorry to interrupt you, please.
Yeah. So right, James Webb, this great new space, often called the Hubble 2.0 or the successor to Hubble. So one of the big differences between Hubble and the James Webb is that the James Webb focuses primarily on infrared light. And something that we glossed over in about a third of a second tonight is that these galaxies that are farther and farther away and moving farther and farther away from us, they're called redshifted. So the wavelength of the light as it moves away from us, it gets longer and longer wavelength, which is what we call infrared. So it goes from visible to the infrared. So some of these most distant galaxies in the universe are actually almost invisible to Hubble because they started in the visible light, but they're moving so fast away, they become infrared. They appear to be infrared. So the James Webb Telescope was designed to see in the infrared. So it's looking for these very, very distant galaxies when they were just kind of forming the first stars in the universe. And that's going to obviously tell us a lot about how our galaxy formed, and how, all of the stars and the planets and everything we see formed. It's like if you were, it's one last story. When I got engaged, my mother-in-law made a photo album of my wife from birth up until that, up until I met her. So of course I only knew her as an adult, but getting to see this photo album of her with baby pictures and kid pictures and all through elementary school, of course it gives me a much better picture and appreciation of her as a person. So I hope she doesn't mind the analogy, but same to these distant galaxies, right? We get to see the baby pictures and their toddler pictures. That's what the James Webb Telescope is going to give us.
Thank you very much. I think this is probably a good place to end the program. I think it was an excellent presentation. Stuart, do you have anything to add at the end? Or no? Okay, so please stay tuned. We have 2 more in the science series. There's a flyer already about it, and God willing, we'll have, as Stuart mentioned, we'll have different programs over the course of the year. Thank you so much, Stuart, and thank you so much, Dr. Schnittman, for a wonderful presentation. Okay, Yasha
Thank you.
Good night to everyone.
Thank you.
תודה רבה. תודה.
Thank you, Stuart.
יישר כוח.
Thank you, Rabbi
Thank you.
Shidman.
Thank you.
Fantastic.